Next up, we're going to talk about kinetic and potential energy. Kinetic movement, potential has the potential to move, right? Can move. First up, we're going to look at kinetic energy. All of this really should be a review from middle school. Anyway, kinetic energy, we use a symbol to represent it of Ke, and basically it's the energy of motion. If anything is moving, you know it has kinetic energy. Kinetic really is just a fancy word for motion. So anything that's moving has kinetic energy. We have the formula for it of Ke is equal to 1/2 of mass times velocity squared. Now, you need to remember some things of order of operation. For instance, you're going to have to square velocity before you can multiply it times mass or times 1/2. 1/2, also remember, it's a lot easier a lot of times to write it in your calculator as 0.5. Also, we might need to solve this for other things, and we can do that. So if we wanted it for mass, it would just be 2 times kinetic energy, because you get 1/2 by multiplying by 2, right? So multiply those two and divide it by the velocity squared. Now, velocity is a little more tricky because it has that square in it. So velocity would just end up being, still have 2 times kinetic energy, and it would be divided by the mass, but all of that would then, you would have to take the square root of. That's what that symbol is, the square root of 2 times kinetic energy divided by mass. Okay? You might want to write those down in your notes because I'm going to expect you to be able to find those on your own from now on. Again, if you're not familiar with the variables, M is for mass, that's in kilograms. V is for speed or velocity, and so that's what that's for, and it's in meters per second. And the overall units for kinetic energy, it's a work, so it's in joules. And so both of these energies are going to have joules. Potential energy is just stored energy. I like to say that it has the potential of moving because it really is just a sitting energy, if you try to think about that. And it has to do a lot with the earth and gravity. So much so that our symbol of PE can sometimes be GPE. Don't be thrown off if you see that. That just means it's gravitational potential energy. But we're going to use PE to represent potential energy, and it's equal to mass times gravity times height. Notice that's little g, the acceleration due to gravity, which we know is a standard. It's 9.8 meters per second squared. Mass is still in kilograms. Height is going to be in meters, the same as distance was, because you're just measuring a distance up is all a height is. Sometimes you will see this formula written where they go ahead and multiply mass times gravity. That gives you the force of gravity, if you remember that from the force unit. So sometimes you can see this written as potential energy is equal to the force of gravity times height, but it's the same thing as that right there. And again, you're going to need to know how to change this around. So if I have mass, that's just going to be my potential energy divided by the acceleration due to gravity times the height. If I wanted to do the height, do that in a different color, then height is just going to be potential energy, need my P, potential energy, divided by the mass times gravity, or the force of gravity. So we could also write that one as potential energy is equal to, or height is equal to potential energy divided by the force of gravity. Both of those are the exact same thing. And again, you might want to be writing those down if you don't want to have to do the algebra to figure that out yourself later. Okay, overall potential energy, like we said, is still a work. Same as kinetic energy, so its units are going to be joules, just a capital J to represent that. Now, last time we mentioned just briefly the conservation of energy, and now we can start to look at that conservation of energy, because remember, energy is not created or destroyed, it just changes form. Well, it's going to change from kinetic energy into potential energy and then back into kinetic energy. Think about this person riding their bike, right? As long as they're moving, even if they're going uphill, they're adding, they have a kinetic energy, right? The higher they go, though, the more potential energy they have. So you might think of them stopping at just a moment at the top. They've put all of this kinetic energy in to get up there, and now all of that kinetic energy is just potential energy. So their energy isn't lost. Every bit of kinetic energy they end up putting in ends up in that potential energy. And so then they can just ride the hill down because the potential energy will turn back into kinetic energy as they move down. And it's a good way to think about this conservation of energy. You're just storing it from one form into the other. And so you would see the levels of kinetic energy are highest here, getting lower and more into potential energy, and now they're highest in potential energy, and then they're changing back into kinetic energy, and then they're the highest in kinetic energy again. Real simple. But this is also a good time to point out that no system is perfect. Now, because no system is perfect, like we talked about before, it only converts energy back and forth in a closed system. But the only closed system we're in is Earth. So even riding a bike, it's not going to have all of your energy go from kinetic to potential. And that's why you get so tired, because you're constantly having to put energy into the bike. The bike's turning into kinetic energy. If you're going uphill, it's turning into potential energy. But that's not all that's going on. No machine is 100% efficient. We're going to learn how to calculate efficiency later on in this unit. But other things are happening. You're producing heat. The bike's producing heat. It's making that clickety sound as you go along. And people can see it, so there's light coming off of it. So heat, light, and sound are all energy that's leaving your system. Now, given they're pretty small compared to the kinetic and potential, so you can still see a good use and a good conversion of that energy. But not all of it's there. And that's what you have to remember, is that not all of your energy goes into that. When you have a car running, you put gas in, but the car vibrates. It has that engine running noise. It has all these moving parts going on inside. And so not 100% of the energy from that chemical energy from the gas ends up going to the kinetic energy of the tires spinning. There's some loss to all of these different things. They're not lost, but converted into these other things. And so you need to remember that term.